Welcome to the deep dive. Ever wonder how all the high-speed bits and pieces in your computer, actually connect and start talking?
It's pretty complex stuff happening behind the scenes.
Right. So today we're diving into exactly that. We're looking at the PCIe link training and status state machine, the LTSSM.
Yeah, the LTSSM. It sounds technical, and, well, it is, but it's fundamental.
Absolutely. Whether you're like a gamer trying to squeeze every drop of performance from a GPU, or you're dealing with massive enterprise servers, knowing how this works is kind of key. It's the negotiator, right?
That's a great way to put it. It's the negotiator, the architect.
Yeah.
It brings that PCIe link to life. It handles the initial handshake, the configuration, keeping the link healthy, adapting it, everything.
Okay, so for this deep dive, what are we really digging into? What are the main stages or concepts we need to grasp?
We'll trace the journey, starting with just figuring out if someone's there, then polling, which is like the first hello and capability exchange. Then configuration, where the link gets its unique address and structure. And finally, L0, the state where data actually flows. That's the goal.
L0, the golden state.
Exactly. But we'll also look at what happens when things need to change, like recovering from errors, changing speed, and this really important process called equalization for the faster rates.
Equalization. Yeah, that's crucial for Gen 4 and 5 speeds, isn't it? And power saving. We can't forget that. My laptop battery thanks PCIe for that, I think.
Definitely. We'll cover the power states. There's L0s, that's like a quick doze. Then L1, which is a deeper sleep. And it even has substates like L1.1 and L1.2 for ultra-low power.
Cheaper sleeps. Okay.
And even L2, L3 ready, which is pretty much hibernation for the link. We'll also touch on, the escape hatches when things go really wrong, like hot reset or disabling the link entirely.
And diagnostics, too, like loop back.
Yep, loop back for testing. And for the real gearheads, we'll get into some advanced stuff like alternate protocol negotiation or APN.
APN, that's how things like CXL can run over PCIe, right, using the same physical wires.
Precisely. It shows how flexible PCIe is becoming.
So by the end of this, we should have a much clearer picture of what's the big takeaway.
I think it's appreciating the intelligence baked into the hardware. These links aren't just dumb pipes. They're constantly negotiating, adapting, optimizing. Understanding the LTSSM demystifies how that incredibly fast, reliable communication actually happens.
All right, sounds good. Let's jump in. Starting at the very beginning, the detect state. What's the first thing the link needs to figure out?
Detect is step 0. It's the state right after a reset, or maybe if there's a link failure. And what's really unique about detect is it's the only LTSSM state where there's no digital chatter, no ordered sets being exchanged yet.
No digital chatter. So how does it even know if another device is connected? Is it magic?
Not quite magic, but it's clever analog stuff happening in the PHY, the physical layer. It's basically feeling for electrical resistance. The transmitter checks if the receiver on the other end has its termination resistors enabled on the lanes.
Okay. So it's like putting a finger out to see if it touches something, electrically speaking.
It's a good analogy, yeah. It's a physical check. Is anyone home?
And there are substates within detect. Detect, quiet, and detect.active.
Correct. It starts in detect quiet. The transmitter goes electrically silent, Feist-Cell-acetyl, as the spec calls it. Yeah. It has to stay quiet for at least 12 milliseconds. Or until its own receiver notices the potential partner stop being idle.
So it listens first?
Essentially, yes. Then, if it hasn't found anyone, it cycles to detect.active. Here, the PHY actively probes, sending out a very low-level signal to check for that receiver termination. It's actively looking now.
Okay, actively probing. What happens then? What are the outcomes?
Well, if it probes and finds nothing, no termination, it just goes back to detect quiet. The cycle repeats.
Right, keeps looking.
But if it detects termination on all the lanes it thinks it could potentially use, that's the signal to move on. The LTSSM progresses to the next major state, polling.
All lanes good, move to polling. Makes sense. But what if it's like a partial connection? Termination on some lanes, but not others?
Good question. That's where it gets a bit more cautious. If it sees termination on only a subset of lanes, it doesn't immediately jump to polling, it waits another 12 milliseconds, then it checks again.
Okay, a recheck.
Yeah. If that same subset of lanes still shows termination after the wait, then it says, okay, this looks stable, and it proceeds to polling, but only using that confirmed subset of lanes.
So it adapts the width right there.
Exactly. But if the set of lanes with termination changes between the first check and the second check, that's unstable. The LTSS assumes no reliable link partner is present and falls back to detect. Quiet to start over.
Wow, okay. That's pretty smart. It really figures out the physical reality first.
It has to. And interestingly, the initial assumption is always to try and use the widest possible link width that both devices might have in common. It can always negotiate down later, but it starts ambitious.
Start wide, then narrow if needed. Okay, so we've detected a partner. We know which lanes seem to be working. We're moving into the polling state. What's the main goal here?
Polling is where the digital conversation begins. The core mission is to establish that initial communication link and exchange some basic capabilities. This is where those spectral packets, the TS1 and TS2 ordered sets, first come into play. Think of them as the first digital handshake.
TS1s and TS2s. Okay, so what kind of info are they exchanging in this handshake?
They're fixed-length packets containing essential stuff, like the link and lane information, though initially it's just placeholder values, their supported data speeds, maybe some status flags or requests. It's like introducing yourself and saying, here's what I can do.
Got it. Introductions and capabilities. And what are the main activities or substates within polling?
It kicks off with polling.active. Here, both transmitters are just continuously sending out TS1 ordered sets. The link and lane number fields are typically set to PAD, which is like a null value. While they're sending, their receivers are listening, trying to lock onto the incoming TS1s or TS2s from the partner.
Listening and sending. What are they trying to achieve specifically in active?
Two key things: symbol lock and block alignment. They need to figure out how to reliably decode the incoming stream of bits on each lane. They also start advertising their supported data rates in those TS1s they're sending.
Symbol lock, block alignment. Basically getting synchronized digitally, right? Speaking the same language at the same rhythm.
Exactly. Symbol lock is recognizing the individual bits. Block alignment is knowing where the groups of bits, the symbols, start and end. It's fundamental for any further communication, like musicians tuning up and finding the beat.
Okay. And then it moves to polling.configuration. When does that happen?
It transitions to polling.configuration once they've had a decent exchange in polling.active. The spec defines it, something like receiving 8 consecutive TS1s or TS2s where the link lane numbers are still PAD, and also having sent a minimum number of TS1s yourself, maybe 10, 24, without any compliance requests interfering. Once those conditions are met, they go to polling.configuration to continue exchanging TS sets and confirm the parameters.
And what about polling.compliance? That sounds different, like a test mode.
You got it.
For
Polling.compliance is not part of the normal link bring-up. It's specifically for electrical compliance testing. It can be triggered by software, or if one side gets a TS1 with a special compliance receive bit set, or sometimes if link training just keeps failing repeatedly.
So it's a built-in checkup for the electrical side of things.
Exactly. The device transmits specific, predefined electrical patterns, like the compliance pattern, jitter patterns, toggling patterns, often at different speeds and equalization settings. Test equipment can then measure these signals to see if the PHY meets the spec's stringent electrical requirements. After running through the patterns, it usually cycles back to polling active to try training again.
Okay, so polling is all about that initial sync up and capability swap. What happens once they've basically agreed on the basics?
Once they're synchronized and have a rough idea of capabilities from polling, the LTSSM moves to the configuration state. This is a really critical phase where the link gets its unique identity within the system.
Identity. What does that mean for a PCIe link?
Primarily, it means assigning unique link numbers and lane numbers. Think of it as giving each side a specific name for this connection and numbering the communication channels between them. It also involves verifying that each of those lanes is working correctly. It's a much more detailed handshake using TS1s and TS2s to ensure both ends agree on the link structure, how many lanes, how they map, and crucially, the link-up signal, the flag that says the day link layer is ready for business, is still firmly set to off 0B throughout configuration.
Still not ready for actual data. Okay, so what are the steps within configuration? How does it assign these numbers?
It starts with configuration.linkwidth.start. Usually the downstream port, that's your root complex or a switch port facing the device, takes the lead. It sends TS1s out on all the lanes it intends to use. These TS1s have the proposed link number, but the lane number field is still PAD. The upstream port, the device itself, responds with its own TS1s or maybe TS2s if it's feeling ready, also using PAD for the numbers.
So the downstream port proposes the width and the unique link ID. What next?
Next is configuration.linkwidth.sept. The downstream port listens for the responses from the upstream port. If it gets valid responses back on a consistent set of lanes, it decides, okay, we can build a link with these lanes. It then internally assigns sequential lane numbers, usually starting from 0 to its end of those active lanes. Once it's figured out its own lane numbering, it moves to configuration.random.length. wait.
Now, wait.
Yeah.
Sounds like it's now telling the other side about the numbers.
Exactly. In lanum, wait. The downstream port sends TS1s again, but this time they contain both the assigned link number and the specific lane number for each lane it just configured. The upstream port receives these and updates its own map. Okay, this physical wire on my side is lane 0, this one is lane 1, and so on.
Got it. And the upstream port needs to confirm it got the message right.
Yeah.
That leads to configuration.lanum accept.
Precisely. In configuration.lanum accept, the upstream port sends back TS1s, or TS2s, echoing the link number and the lane numbers it has now accepted and configured on its side. The downstream port receives these and compares them to the numbers it sent out.
Okay, comparison time. What if they match? What if they don't?
If they match perfectly, great. The LTSSM proceeds to configuration.complete. The spec also allows for lane reversal, so if the numbers match but are in reverse order and reversal is supported and enabled, that's also okay.
And if there's a mismatch?
If there's a mismatch, but the downstream port thinks a narrower link is still possible, using a subset of lanes that did respond correctly, it might try reassigning lane numbers for that smaller width and loop back to configuration.lanum, wait to try again. But if the mismatch is bad or not enough lanes are working, configuration fails. The LTSSM has to give up and go all the way back to detect to start the entire process over.
Wow, quite a negotiation. It really ensures both sides have the exact same map of the connection.
It absolutely has to. So assuming they finally agree in lanum, except they move to configuration.complete, what happens there?
Complete sounds like the final confirmation.
It is. It's the last handshake in this phase. Both sides continuously send TS2 ordered sets now. These TS2s contain the final agreed-upon link and lane numbers. To get out of this state, each side needs to send a bunch, at least 16 after receiving one, and receive a string, like 8 consecutive, of matching TS2s from the partner.
Almost there. What's the very last step before L is 0?
The final tiny step is configuration.idle. Here, both sides start sending electrical idle ordnance sets IDLEs. This signifies the end of the PHY configuration. It's like saying, okay, physical layer setup complete, we're ready.
And then we finally reach L0, the operational state.
Yes. After that IDL exchange and configuration, idle meets its criteria, like sending 16 after getting 1, receiving 8 consecutive. The LTSSM transitions to L0. This is where the data link layer finally comes alive, the link up variable flips to 1B, and actual data packet CLPs and DLLPs can start flowing. It's the golden state.
The golden state, love it, but links don't always stay at their initial speed, right? What if they want to go faster?
Good point. That's where the recovery state comes in. L0 isn't necessarily static. The link can enter recovery for a few key reasons. Definitely to change speed if both devices support faster rates, but also to retrain the link if errors start creeping up in L0, or critically for higher speeds to perform equalization tuning.
Okay, so recovery is like a pit stop for adjustments. How does a speed change typically work within recovery?
Well, first, something needs to trigger. It could be software saying go faster, or maybe the hardware automatically decides to try. This bumps the LTSSM from L0 into recovery. Inside recovery, you have subskates like recovery.rcvr lock and recovery.rcvr cfg. The first goal is just to reestablish lock, exchanging TS1s and TS2s, but still at the current speed.
So resyncing first.
Right. Then, during recovery.rcvr cfg, the side wanting to speed up will usually set a speed change bit in the TS1s it sends. It's basically advertising, hey, I can go faster, you.
An advertisement. Okay.
If both sides agree they can and want to go faster, they move to recovery speed. Here, they negotiate and settle on the specific new target speed. Once agreed, the PHYs physically change their clocks and electricals to match the new rate.
And then, does it go straight back to L0?
Not necessarily. If the new speed is 8 gigatransfers per second or higher, there's a mandatory detour, recovery equalization. We need to tune the signal for that speed. Only after that is done successfully, or if it wasn't needed for speeds below 8 GTs, do they exchange IDLEs at the new speed and transition back to L0, but now operating faster.
Equalization. Right. What if this whole recovery process fails? Like they can't agree on a speed or equalization doesn't work out.
Yeah, failure is an option. If things go wrong in recovery, maybe the signal quality is just too poor at the higher speed even after equalization, or they can't lock properly. The LTSMM might try to fall back to a previously known good speed. If it's a really bad failure, it could even punt all the way back to detect and force a full retrain from scratch. So recovery is this essential intermediary state for adapting the link, but stability is always the priority.
Okay, you mentioned equalization is critical for 8 GTs and up. Can you remind us why it's needed? What problem is it solving?
Sure. As you push signals faster and faster down those copper traces on the motherboard, the channel itself starts acting like a filter, specifically a low-pass filter. It eats away at the high-frequency parts of the signal.
Okay, it muffles the sharp edges of the signal.
Exactly. And that muffling causes the signal for one bit to kind of smear into the time slot for the next bit. This is called intersymbol interference, or ISI. It makes it harder for the receiver to tell a 1 from a 0, which increases the bit error rate, the BER. Equalization is the set of techniques used by both the transmitter and receiver to fight back against this signal degradation caused by the channel.
So it's like noise cancellation and signal boosting specifically for high-speed data.
That's a pretty good way to think about it. It's a cooperative effort. On the transmitter side, you have TXEQ transmit equalization. This involves things like de-emphasis, where you slightly lower the voltage for consecutive identical bits, and pre-shoot, where you slightly boost the voltage just before a bit flips.
Pre-distorting the signal so it arrives cleaner.
Precisely. It's often done with a digital filter, like a 3-tab FIR filter for Gen 325. The spec defines standard presets, which are just combinations of these filter settings. On the receiver side, you have RxEQ receive equalization. This might involve CTLE, continuous time linear equalization, which is like an analog amplifier for high frequencies, boosting what the channel attenuated.
Okay, boosting the highs.
And often, DFE decision feedback equalization. This is clever digital filtering, where the receiver uses the bits it just decoded successfully to predict and subtract the ISI they're likely causing on the current bit being decoded.
Using past bits to clean up the present bit.
Cool.
So the goal is to tune all these TXEQ and RxEQ knobs.
Right. The whole point of the recovery equalization state is for the two link partners to negotiate and find the best combination of TXEQ and RxEQ settings to get that bit error rate down to the incredibly low level required by the spec, like 10, 12 or better.
And this happens in phases, you said. Phase 0, 1, 2, 3.
Correct. For 8 GTs and up, it's typically a structured multi-phase process within recovery. Equalization, using TS1s and TS2s to communicate.
Let's walk through them. Phase 0.
Phase 0 is mostly relevant when you're first moving up to ATTs from a lower speed like 2.5. The upstream port basically tells the downstream port, hey, I want to go to 8 giga, and here's a suggested starting TXEQ preset for you to use when you get there. This message is actually sent at the lower speed.
Okay, sending advice before the jump.
Yeah. The goal is just to get a basic, somewhat functional link at 8 GT so they can start the real tuning. The USP waits for the DSP to acknowledge it's made the speed switch before moving to phase 1.
Got it. Phase 1, now they're both at the target speed.
Yes. Phase 1, both are running at the higher speed, say 8 GTs. They exchange TS1s to advertise their full EQ capabilities, what presets they support, etc. They evaluate how well that initial preset from phase 0, or default, is working. The DSP might ask the USP to try a different preset. If, miracle of miracles, the signal quality is already good enough, BER 1012, they can actually signal EQ complete using the EC field in the TS1 and exit straight to L0.
Ah, an early exit possibility. Nice. But usually they need more tuning.
Often, yes. If more tuning is needed, they'll indicate in the TS1s that they intend to proceed to phases 2 and 3.
Okay, phase 2, who's tuning what?
In phase 2, the downstream port takes charge of optimizing the signal it's receiving from the upstream port. The DSP analyzes the incoming signal and uses TS1s, or special EQ TS2s, to request specific changes to the upstream port's TXEQ settings, try this coefficient, use preset 5, etc. At the same time, the DSP is also tuning its own RxEQ to best decode whatever the USP is sending. It's iterative, within a time limit.
The DSP tells USP how to transmit better, while DSP also adjusts its own receiver.
Exactly. Once the DSP is happy with the signal coming from the USP, it signals phase 2 is done, and then the roles flip for phase 3.
Makes sense. Phase 3 USP takes the lead.
Yep. Now, the upstream port optimizes the signal it's receiving from the downstream port. It requests changes to the DSP's TXEQ via TS1 SEQ TS2s and simultaneously tunes its own RxEQ, again, within a time limit. If, after phase 3, both sides are happy with the signal quality in both directions, they exchange final TS2s confirming the chosen EQ settings, then exchange IDLEs or flits in newer specs, and finally transition to L0 at the higher speed, fully equalized.
That is a seriously detailed back and forth. It must ensure a really robust link.
It has to, especially as speeds climb. It dynamically adapts to the unique imperfections of every single channel.
Now, with Gen 4 16 GTs and Gen 5 32 GTs, did this process change much? Did it just get longer?
Good question. For Gen 4 16 GTs, it builds on the 8 GTs process. Typically, you'll first train fully to L0 at 2.5, then do the full EQ phases 0-3 to get to L0 at 8.0 GTs. Then to get to 16.0, one side re-enters recovery, and optimization exists. If both sides already successfully reached 8.0 GTs L0 and both support 16.0, they can often skip phase 0 for the 16.0 GTs equalization and go straight into phase 1 at 16.0 GTs. Saves a bit of time.
Okay, skipping phase 0 for 16 giga. What about Gen 5 at 32 giga? That sounds like it could take ages doing EQ at 8, then 16, then 32.
It could. That sequential approach, 2.5 minus 0 minus EQ minus 8.0 minus EQ point minus EQ point minus EQ minus EQ minus 32.0 is the conventional full equalization. And yeah, it can take hundreds of milliseconds. So PCIe 5.0 introduced optional equalization bypass modes to speed things up.
Bypass modes. Tell me more.
Two main ones. Bypass to highest rate lets the link jump from, say, 2.5 GTs directly to the highest speed both support, like 32.0 GTs, and only perform the full EQ process at that final speed. Much faster link training.
Okay, one big jump, one big EQ session. What's the other?
The other is no equalization needed. If both sides support this mode, and crucially, if the channel is known to be very good, maybe super short traces or it's been pre-characterized, they can agree to skip the equalization phases entirely.
Skip EQ altogether. How do they know the settings then?
They'd likely use predetermined settings, maybe golden values stored in firmware or non-volatile memory from previous training or system characterization. This is really for well-controlled environments. Both these bypass modes are negotiated during the configuration state using capability registers and signaling within the TS1, TS2 packets.
So the link can decide early on if it thinks it can skip parts of the EQ dance. Very efficient.
Exactly. Balancing robustness with faster boot wake times is always a goal as speeds increase.
We've covered speed changes and EQ and recovery. What about changing the width of the link, the number of lanes after it's already up in L0? Does recovery handle that too?
Not primarily, no. The main negotiation of link width happens back in the configuration state, remember. Configuration.linkWidth. Start laneimum. Wait, except that's where the number of lanes is really decided and numbered.
Right. Configuration sets the initial width, so recovery is more about...
Recovery is mostly about maintaining stability on the existing lanes, handling speed changes, and doing equalization for those lanes. It's not really designed for fundamentally renegotiating a different number of lanes.
So if you do need to change width after L0, say drop a lane that's become unreliable, or maybe software wants to force a narrower link for power, how does that happen?
For significant changes like that, especially if it involves dropping lanes or needing to reevaluate which lanes are usable, the LTSSM usually has to go back further than just recovery. It might re-enter recovery briefly, but often it needs to go back to configuration to properly renegotiate the width and renumber the lanes. In some cases, especially if directed by software or due to major errors, it might even need to fall all the way back to detect and start the whole training over from scratch.
Back to detect. Ouch, that sounds slow.
It can be. That's why initial configuration tries to get the width right. Now, there is a newer mechanism in PCIe 6.0 called L0P.
L0P, what's that?
It's a state that allows for dynamic width changes, adding or removing lanes directly within L0, mainly for power saving. It's much faster than a full retrain. But L0P isn't for the initial width negotiation or for recovery from major errors needing a full renegotiation. It's more about agile power management on an already stable link.
Okay, so summarizing width changes. Initial setup is configuration. Recovery keeps the current width stable. Big changes usually mean going back to configuration, maybe via recovery or detect. And L0P is a newer, faster way for dynamic changes in Gen 6 plus Aero.
That's a perfect summary.
Great. We've hit the core states and recovery. Let's explore some of the other key LTSSM states. L0. L0 standby. What's its deal?
L0s is a mandatory state. Think of it as a very, very light nap for the link. It's designed for extremely short periods of inactivity, offering minimal power savings, but with super fast entry and exit.
A quick power nap. How does it decide when to nap?
It's autonomous. If a transmitter finds itself idle for a pre-agreed short time, it can just decide to enter L0s for its direction. It sends a quick signal in EIOS, electrical idle ordered set, and then puts its transmitters into electrical idle. Importantly, one direction can be in L0s while the other is still active in L0.
Independent naps. How does it wake up so fast?
To wake up, the transmitter just needs to send a specific number of special patterns called FTS fast training sequences, followed by a skip ordered set. The receiver needs these FTSs to quickly relock onto the signal. How many FTSs are needed NFTS is actually advertised by the receiver during initial training.
The receiver says how long the wake-up call needs to be.
Pretty much. More FTSs means easier lock, but slightly longer wake-up. It's a trade-off. But we're talking sub-microsecond exit times usually. It's really fast because it avoids a full recovery cycle. Just turns off the transmitter briefly. Perfect for those tiny gaps in traffic.
Okay, L0s is a quick nap. Now, L1 sounds like a deeper sleep.
It is. L1 offers significantly more power savings than L0s, but the trade-off is longer wake-up latency. And unlike L0s, when a link enters L1, both directions go together.
How does it get into L1? Is it automatic like L0s?
It can be. There's ASPM L1 active-state power management. This is optional hardware-driven entry. Typically, the upstream port, like your graphics card, notices things have been idle, usually after L0s in both directions, and asks the downstream port, the chipset CPU, for permission to enter L1. If the DSP agrees, they both send EOS and go idle.
Ask for permission. Can it be denied?
It can, yeah. If the DSP needs the link soon, it might reject the request.
Yeah.
The other way is PCIe L1 software initiated. The OS tells the device go to low power state D1, D2, D3 hot, and that triggers the link to enter L1. Software requests are usually not denied.
Got it. And then there are L1.1 and L1.2, even deeper sleep.
Exactly. These are L1 substates, mainly for mobile battery devices offering even lower power. They involve an extra out-of-band signal, CLK-REQ shag, to talk to the system's clock controller. When entering L1, the device drops CLK or AQ shag, signaling the main reference clock could potentially be turned off.
Turning off the clock saves more power. What's the difference between L1.1 and L1.2?
In L1.1, some basic voltage levels, common mode, are kept alive, but the high-speed stuff like PLLs are off. Power drops a lot, maybe 120th of L0, and wake-up is around 20 microseconds. L1.2 goes further, everything high-speed is off, including voltage keepers. Power can be incredibly low, tens of microwatts, but wake-up takes longer, maybe 100 microseconds.
Okay, power versus wake-up time, how does it wait from L1? Is it like L0?
No, it's slower. For legacy L1, if either side needs to send data, it triggers an exit, but this forces the link into the recovery state for a full retrain. The receiver detects the idled exit, often a TS1, and jumps to recovery. For L1.2, the device first has to reassert CLK-REQ shag to get the reference clock turned back on. Once the clock is stable and PHY is power up, then it goes into recovery for retraining. So any L1 exit means a recovery cycle, unlike the instant wake-up from L0s. That's why latency tolerance reporting, LTR, is important. Devices tell the system how quickly they need to wake up, influencing which L1 state is appropriate.
Recovery after L1? Makes sense. Okay, now for the really deep sleep, L2 or L2, L3 ready.
Right. L2 is very low power. Main transceiver power is usually off. It often corresponds to the D3 cold device state, where maybe only a tiny bit of auxiliary power, those have kept on. L3 is everything off, completely powered down. L23 ready is the LTSSM state, signifying the link is preparing to enter L2 or L3.
How does it get there? Software again.
Primarily software-driven, yes, like putting a device into D3 cold. The link usually goes through L1 first to idle the transceivers gracefully before main power is cut for L2.
And waking up from L2, with the main power off, how does it even get a signal?
Good question. If VOS is present, L2, it needs a special wake-up event, either a dedicated sideband signal called wake shag, if the system supports it, or an in-band signal called beacon.
Beacon, what's that?
Beacon is a very low-frequency signal, kilohertz or low megahertz range, sent on lane 0. It's slow enough to be detected by the minimal circuitry kept alive by VO. Once a wake event happens and main power clocks are restored, the LTSSM has no choice but to go right back to detect and start the entire link training from scratch.
And from L3, where all power is off.
From L3, exit is a cold reset. It's like powering the system on always starts at detect. So L2, L3 offer the absolute maximum power savings but incur the longest wake-up latency because of the power restore and the mandatory full retrain from detect.
Deepest sleep, longest wake-up. Got it. Let's switch to error recovery now. Hot reset, what is that exactly?
Hot reset is an in-band way to force a full reinitialization and retraining of the link. It's like hitting a reset button specifically for that PCIe connection without needing a full system power cycle. The link goes down momentarily and then attempts to retrain from the beginning.
When would you use that?
It's for recovering from more serious link level errors, where maybe just going into recovery isn't enough, or if software explicitly wants to force a reinitialization of the link.
How is it triggered?
Two main ways. Software can trigger it often by writing a bit in a bridge control register somewhere up the hierarchy, or it can be signaled in-band. If a port receives 2 consecutive TS runs with a special hot reset bit set, it initiates the reset. The port sending those TS1s is already in the hot reset LTSSM state.
And what happens to the LTSSM?
It goes into a dedicated hot reset state, like 0 by 211, and from there, it must proceed directly to detect. It forces a full restart. Detect UGMA and OCK polling configuration -0. For the device, this often resets its link layer state too, potentially losing its configured bus device numbers, so software might need to re-enumerate it after it retrains.
So it's a pretty forceful reset, but still avoids a power cycle.
Exactly. It's a powerful recovery tool. Forces a clean slate negotiation with speed, EQ, everything.
Yeah.
Higher chance of recovery than just entering the recovery state.
Okay. What about the link disable state? Sounds pretty final.
It is. Link disable means the link is intentionally shut down. Non-operational, no training, no data. PHY is powered down or in very low power.
How does a link get disabled?
Primarily software. There's usually a link disable bit in a control register that software can set to explicitly turn the link off. It's less common for the LTSSM to autonomously decide to enter disable, but maybe after repeated persistent training failures, some implementations might fall back to a disabled state as a last resort. Some diagrams show paths to disabled states from various timeout conditions.
And the implications, link is just off.
Yep, link down, link up signal is off. Device might lose context, no packets flowing. PHY is effectively off.
How do you get it back?
Only way out is software intervention. Software has to explicitly clear that link disable bit.
Does it just resume?
No, clearing the disable bit forces the LTSSM back to detect. It needs to retrain completely from scratch. So link disable is the definitive off switch, used for power management, resource control, or handling faulty links, but re-enabling always incurs the full training latency.
Okay, the off switch. One more state. Loopback. That sounds like a diagnostic.
It is.
Yeah.
Loopback is purely for testing and fault isolation. One side acts as the lead, or master, sending data, and the other acts as the follower, slave, receiving the data and immediately sending it right back.
What does that test?
It tests the whole round trip. Lead's transmitter, the channel to the follower's receiver, the internal path within the follower to loop the data back, the follower's transmitter, the channel back to the lead, and finally the lead's receiver. It's a pretty comprehensive check of the PHY in the near-end channel.
How do they get into this mode?
The lead initiates it by sending TS1s with a loopback bit set. When the follower sees two consecutive TS1s like this, it enters loopback entry, gets ready, then goes to loopback.active. The lead waits for the follower to signal it's active before sending test data.
And the follower just echoes everything back.
Exactly. It receives on RX, transmits the same data on TX. It might also need to handle clock differences using skip-ordered sets.
How do they exit loopback?
The lead sends an electrical idle ordered set, EIOS. When the follower detects the EIOS, both sides exit the loopback state.
And after exiting, back to detect again.
Typically, yes. After loopback, the link needs to retrain, so it usually goes back to detect. There's also a newer thing in Gen 6 called DNALB Digital Near-End Loopback, which gives more granular control over internal loopback paths within the PHY itself, useful for manufacturing tests. But the standard LTSSM loopback is a powerful diagnostic for the whole link path.
Very useful for debugging. Okay, let's shift to the really advanced features. Modified TS1, TS2 ordered sets. What are these?
They're basically standard TS1s and TS2s, but with some fields repurposed to carry extra information beyond basic link training. Their main job right now is alternate protocol negotiation, or APN.
APN using the PCIe wires for something else, like CXL.
Exactly. APN allows devices that support both standard PCIe and an alternate protocol, like CXL, to figure out which protocol they should use over that physical connection.
Right.
The modified TS1, TS2 packets carry the negotiation messages for this.
How do they know to use modified TS instead of regular TS?
Devices advertise support for APN in their configuration registers. There's also usually a control register setting to tell the LTSSM, okay, use modified TS for this training session, specifically for APN. The actual alternate protocol data, like I support CXL.mem version 1.1, is loaded into specific data registers that get packed into the modified TS1, TS2 payload.
And when does this APN happen during LTSM?
It happens relatively early during the configuration state, specifically in substates like lanum.accept and complete. This is before the link ever gets to L0 at Gen 1 speed.
How does the negotiation work?
It's usually a two-phase process within configuration. Phase 1. Both sides exchange modified TS1s, advertising what alternate protocols and features they support, like CXL capabilities. Phase 2. The downstream port usually looks at the capabilities, decides on a common protocol, and sends a modified TS2 proposing it. The upstream port confirms by sending back the same modified TS2. If they agree, APN succeeds.
And they finalize this before reaching configuration to complete?
Typically, yes. If APN succeeds, they might agree to operate as, say, a CXL link. If it fails, no common protocol or mismatch, they might fall back to standard PCIe operation, or in some error cases, maybe even back to detect.
So this is how a physical PCIe slot can magically become a CXL connection.
That's the magic, yes. APN, using modified TS packets during the configuration state, allows that flexibility. It lets CXL and potentially other future protocols leverage the existing robust PCIe PHY layer without needing entirely new physical interfaces. It really shows how PCIe is evolving into a foundational interconnect technology.
That's incredible flexibility. Wow. Okay, we've covered a huge amount of ground here, from basic detection all the way to these advanced protocol negotiations. This has been a fantastic deep dive into the PCIe LTSSM. Any final thoughts to wrap this up?
Well, I think the main thing is just the sheer elegance and complexity of the LTSSM. It's this incredibly sophisticated state machine that underpins so much of modern computing. It handles everything from that first electrical handshake to ensuring signal integrity at insane speeds, managing power, recovering from errors, and even adapting to run different protocols. It's constantly evolving too, keeping pace with technology demands.
It really makes you pause and think about the insane amount of negotiation happening constantly inside your machine just to make everything work together seamlessly.
Absolutely.
Oh.
Every time you connect something, every time you boot up, this intricate dance is happening. It's a testament to some brilliant hardware design. And, for anyone whose interest is piqued, the actual PCIe specification is out there. And exploring technologies like CXL that build on this foundation is definitely worthwhile.
Fantastic advice. Well, that brings us to the end of this deep dive. Huge thanks for walking us through the fascinating world of the PCIe LTSSM, and thank you all for joining us. Until next time.